For today's lesson, we are going to be covering one of the most fundamental topics in all of mathematics, and that is the notion of an equivalence relation. At its core, the definition is rather simple. We have a relation on a set A. We say R is an equivalence relation on A if it is reflexive, symmetric, and transitive. In our last lesson, we considered one such relation, equality, which is rather dull. But today we will actually be studying two equivalence relations. One will allow us to define the rational numbers as a set, and the other relation we will study is what is known as the integers modulo n, which gives rise to modular arithmetic, which we'll consider in further detail later in the course. Now, I am going to do things differently than the book for this lesson. I'm going to start off with two examples of equivalence relations and then move to the theory. Which brings me to the exam on Monday. In my email, I said that the exam will cover through 4.5, but that is not entirely accurate. The only aspects of 4.5 that I will ask you on the exam is how to verify if something is an equivalence relation or not. In other words, is a relation reflexive, symmetric, and transitive? And the definitions that we are going to consider right after this, which is the set of equivalence classes. And the rest of the theory, that will not be tested upon. And so let us go ahead and get started. And I want us to consider a question that was posed at the beginning of the term. How do we define the set of rational numbers? In that lesson, I gave the following set, which I'm going to write as Q tilde, where we have the set of A over B, such that A and B are integers, and B is not equal to 0. Is this the set of the rational numbers? At first glance, it looks like it is, until we remember how we define elements to be equal to in a set. And that's where we run into trouble. Because in Q tilde, we have that 1/2 and 2/4 are elements by definition. But 1/2 does not equal 2/4. Because in the definition of the set, they are considered as distinct elements. And that is a problem when defining the set of rational numbers. And so Q tilde is not the set of rational numbers for that reason. Okay, well, let's think about what are the defining features for rational numbers. And so I'm going to put this separate and change the color. So now, if we had in the set of rational numbers A over B and C over D, and we knew that A over B was equal to C over D. What does that tell us about the two fractions? What is their defining feature? Well, if we cross multiply, we have that this is equivalent to the equality AD equals B times C. And we see it right here. 1/2 is equal to 2/4 in the rational numbers. And if we cross multiply, we have 1 times 4, 4, 2 times 2, 4, and we have that equality. And so that's what we want to focus on. We are going to construct an equivalence relation on Q tilde. And so here it is. So let's go ahead and call it R. Let R, actually let me write this as a theorem. Let R be the equivalence, let R be the following relation. So it's a relation on Q tilde, and it's going to be A over B, comma C over D, in Q tilde squared. And then we have the property that AD is equal to BC. So this is a subset of Q tilde squared, so that means that R is an equivalence relation on Q tilde. And what the theorem has is that then R is an equivalence relation on Q tilde. I'm not going to do the whole proof. I'm going to leave reflexive and symmetric as an exercise. So the case of reflexive and symmetric are left as an exercise. And what we are going to do is do transitivity. Well, for transitivity, we go back to the definition and recall that to prove that something is transitive, that a relation is transitive, we want to choose, so it's for all x, y, z in that set, and so we want to choose arbitrary x, y in the relation and y, z in the relation, and then show that x, z is also in the relation. And so that's what we are going to do. But now, since we are working with Q tilde as our set A, the x, y, and z are going to be fractions of integers, where b, of course, where the denominator, of course, is non-zero. So let's go ahead and do that. So let's go ahead and let A over b over c over d, and so this is our x, y, and now we're going to choose our y, z. And so now we have c over d, and e over f, b and q tilde, sorry, not q tilde, in R. So it's in our relation. So in particular, since we have that a over b and comma c over d is in R, we have that AD is equal to BC. So we have AD is equal to BC, and we also have the same over here. We have C times F is equal to D times E. So we got this. And what we want to show is that A over B, comma, E over F is in R. And so I'm going to put this in over here, scratch work. So we want to show that A over B, comma, E over F is in the relation. But to do this, it suffices to show that AF is equal to B times E. Now the way we are going to show this is by solving for C here and then plugging in. And so note, I'm going to come back to the proof. Thus, C is equal to DE over F. And now here we are implicitly using the fact that F is non-zero. Because to be in Q tilde, E over F is in Q tilde, and so F is non-zero. And so I'm going to go ahead and put it over here since F is non-zero. So we can do that. Now observe that if we go from AD is equal to BC, since now we have that substitution, we have that this here is AD equals BC, which is now DEF, DE over F. And now if we go ahead, cross multiply, we have AD over F. The F comes over to this side, and now this is BDE. And we know that D is also non-zero. So we can go ahead and divide by D. And so we have AF equals BE, since D is non-zero. But that is what we wanted to show. Now we have this. So in particular, we have that A over B, comma E over F is an element of R, which shows that R is transitive. And we are done. So we have now shown that. And if we assume the statements that were left as an exercise, that is reflexive and symmetric, we now have that R is a equivalence relation. On Q tilde. Well, as of right now, this doesn't seem to be getting us. Sure, we have this relation, but how does that give us how to construct the set of rational numbers? And to that, we turn to our next definition. So if we have a equivalence relation on a set A, and we have that X is in A, we define the equivalence class of X with respect to the relation R to be the set bracket X subscript R, and that's the collection of all Y in A such that Y is related to X. Whenever R is clear from context, we drop the subscript. And then we define the set of all equivalence classes of elements of A under that equivalence relation to be A modulo R or A mod R. So in Bellman, he says A modulo R. Oftentimes we simply just say A mod R. So let's put all this together because there's a lot of notation here. So let's see what all of this means with what we just saw with the relation R on Q tilde. So first thing to consider is, what is an equivalence class? Well, according to this, we can choose any X. For every X in A, there is some equivalence class corresponding to it. And so let's go ahead and choose 1/2. So let 1/2 be in Q tilde. So now, if we were to look at the equivalence class of 1/2 under our equivalence relation R that we just considered, we then have that by definition, the equivalence class 1/2 R is the set of all Y in A, or Y in Q tilde. And so, because we know that Q tilde is a set of fractions, I'm going to just simply write this as C over D in Q tilde, such that C over D is related to 1/2. But now we know what it means to be related. And so we can go ahead and simply write this as those fractions C over D in Q tilde, such that 2 times C is equal to D. And we can go ahead, and that's now using our definition of what it means to be, for two elements to be related in this equivalence relation. But we can go one step further. If 2C is equal to D, we can come back to our choice of Q tilde, which we had some arbitrary C over D and Q tilde satisfying this property, and substitute that in for D. And so now we have C over 2C in Q tilde is the set, is the equivalence class for 1/2 under the equivalence relation R. Now, something to be mindful of here. our experience with fractions makes us want to cancel off the c's. But we are working in Q tilde, where this here, if we were to cancel off as we normally would, it's not the same as 1/2 because we're writing distinct elements of Q tilde. And so that's just something to be mindful of here, is that we don't want to cancel these off. But either way, we now have that 2/4 is in here. If we plug in c is equal to 2, we get 2/4. We also have 3/6, and so on and so forth. And so we see that this here, 1/2 r, is encompassing all the fractions that we know are equal to 1/2. But now we have this as a in set notation. So that's the first definition. So that's defining the equivalence relation. Now let's look at this A modulo R. So in this case, we're looking at Q tilde modulo the equivalence relation, and this is the set of all C over D in R, where C over D is in Q tilde. Now I keep writing C over D, but we don't have to. We can simply just go ahead and write this in the equivalence class of X. X is in Q tilde, and by X being in Q tilde, it is going to be equal to some C over D. And so we got this here. And so that's our definition. Now, this second portion is keeping in mind that X that the equivalence class is a set. And so we can also think about that as those subsets of Q tilde such that there exists some X in Q tilde. And actually now, since we're working with lowercase, I'm going to switch it to a lowercase y in Q tilde such that X is equal to the equivalence class of y under that equivalence relation. And so that's what this is getting at, is that we can also think about it from this point of view. We are looking at those subsets such that X is equal to some equivalence class for some element of Q tilde. It is this set, Q tilde mod R, that we define to be the rational numbers in mathematics. Whenever we say 1/2 or 2/4, 3/6, we know in our minds that these are all the same exact rational number. From a set theoretic perspective, we are actually not, whenever we say 1/2 or 2/4 or 3/6, we actually are thinking the equivalence class of 1/2 under that equivalence relation R. And similarly, since 1/2 is the same as 2/4 R, which is the same as 3/6 R, they are the same exact set, then now we have that this matches up with our intuition. The next thing you may ask is, well, how does one define addition, multiplication for sets? And we can, and we will. And so we're going to see an illustration of how we can define addition and multiplication in a way that is what we will call well-defined. And so that is to come. So next we are going to fix a positive integer m, and we are going to say that two integers x and y are congruent modulo m if there is some k such that x minus y is equal to k times m. In other words, m is a factor of x minus y, or said differently, m divides x minus y. We will use the notation x and then this symbol here, which we read as congruent. And so verbally, this symbol is telling us x is congruent to y modulo m. In my lectures, I'm going to simply write x is congruent to y mod m and drop the parentheses, which Belleman does use in his text. Now, this simple definition was first introduced by Gauss in his Discusiones Arithmeticae from 1801. In this book, Gauss changed number theory, revolutionized it, and that's putting it lightly. In it, he was able to go back and prove results that had already been done in number theory up to that point in a simpler way. And also prove a conjecture of Euler from 1744, which is now known as the law of quadratic reciprocity, which Gauss called his golden theorem. And so we're going to be coming back to modular arithmetic later in the course, as this is fundamental for proving number theoretic results. But what we are going to do is prove first that this here is an equivalence relation. And so the theorem is as follows. For every positive integer m, congruence modulo m is an equivalence relation on the integers. And so now this symbol here, I'm going to be referring to it as congruence modulo m, is the set theoretic definition of the relation. And so here we have, it's the set of ordered pairs, x comma y, in the Cartesian product of the integers with itself, such that m divides x minus y. So let us go ahead and go through the ideas here for the proof. Now, for the proof here, I'm not going to go through the whole details. Transitivity is done in the text. So, our text does transitivity. And so what we are going to do is prove that it is reflexive and symmetric. So let us first do reflexive. So we show that congruence modulo m is reflexive and symmetric. So for reflexive, what we need to do is show that for every integer x, we have that x comma x is in Z2. So let x be an integer. Then x minus x is equal to 0, which is 0 times m. Therefore, x comma x is in the relation congruence modulo m for each integer x. Thus, congruence modulo m is reflexive. So it remains to show that it is symmetric, and for symmetric, we need to choose x comma y to be in the congruence. So next, let x comma y be in the congruence modulo m relation. So this is equivalent, by definition, to x minus y is equal to km for some integer k, but then if we multiply by -1 on both sides, we end up getting that this is y minus x is equal to -k times m. And I'm going to go ahead and just put parentheses around the -k. But now if we have this is equivalent to y comma x being in the relation. So hence y comma x is in the relation congruence modulo m, which shows that congruence modulo m is symmetric and thus transitive. And thus an equivalence relation. It definitely does not show that it's transitive. And so we're done. But again, here we did not show transitivity. That is done in the text, and so I leave it to you to read the portion for transitivity. But once we have that, we have its transitive, symmetric, reflexive, and equivalence relation. So now let us come back to our definition for equivalence class. and what it means to have a set modulo an equivalence relation in the context of the integers under the equivalence class of congruence modulo m. So let's go ahead and fix m to be 5. And let us consider the congruence relation 5, which is now the set of tuples x comma y in the Cartesian product of the integers with itself, such that x minus that 5 divides x minus y. And so that's the definition. And instead, so here's just a symbolic definition. Let us do a concrete example. What if we wanted to know what the equivalence class of 3 was? Well, if we look at this equivalence class, well, what is it? By definition, this is the set of y in A, and so those integers y, such that y is related to 3. And so we have y is under this relation to 3. But I'm going to write this differently. While this is the definition of the relation, we don't write this notation but use the mod notation that was mentioned here. And so I'm going to go ahead and rewrite this as y is congruent to 3 mod 5. So what is this? Well, if we dig deeper, we have now, by the definition of congruence, so by definition, we have that there exists some k in the integers such that y minus 3 is equal to 5 times k. But now, if we go ahead and rewrite that part of the set and rearrange it, we get that this is those y's such that y is equal to 3 plus 5k. So in other words, this set is a set of y's such that if we divide by 5, the remainder is 3. Because we have it now in the context of the division theorem. We have our 5 times k, so we have our y is taking the role of a in the division theorem. Our 5 is taking the role of the of b, and now k is the quotient, and 3 is the remainder. And so we are now looking at this in terms of remainders. And so we're going to come back to this in more detail later. But what I want to emphasize for now is that with this reasoning, we now get that the integers modulo the congruence 5 is going to be the equivalence class of 0, the equivalence class of 1, equivalence class of 2, 3, and 4. Because the remainder will have to be always less than 5. And so we have 4. And so there are just 5 elements in here. Also, this notation is not common. In abstract algebra, you'll be introduced to this notation. Some texts also write this as z sub 5. And so depending on the text, these are the two notations you'll experience for the integers modulo 5, or modulo m more generally. Now we are going to move towards the theoretical portion of 4.5, and so we begin with the following definition. Suppose A is a set, and let F be a subset of the power set of A. Now, this statement here is telling us that F is a family of sets. Because if we were to take some x in F, Since f is a subset of the power set of A, that tells us that x is an element of the power set of A. But x is an element of the power set of A if and only if x is a subset of A. So in other words, f is going to be a set of subsets of A. And so it is a family of sets. So with that, we're looking at some family of sets whose elements are themselves subsets of A. And we say that f is pairwise disjoint if every pair of distinct elements of f are disjoint. Or in other words, if we take every x and y in f such that x is not equal to y, then that implies that the intersection of x and y is equal to the empty set. So they have no elements in common. We say that f, and there's a typo here in here, so this is script f. So we say that f is called a partition of A if the following three properties hold. If we take the union of the family of sets, then that is equal to A. We have that f is pairwise disjoint, and for every x in the family of sets, it is the case that x is not equal to the empty set. So let us consider an example. So now we are going to be looking at the set A. This is the set 1, 2, 3, and we have three different families of sets whose elements are subsets of A. So we have F. This consists of 1, 2, the set containing 2 and 3, and the set containing 3. We have G, has the empty set, it has 1, it has 2, and the set containing 3. And we have finally H, the set containing 1, and the set containing 2 and 3. So let's see which of these is a partition of A. So let's begin with F. So if we look at F, in here we take the union of F, and if we take that union of the families of sets, that's the union of the set 1, 2, union 2, 3, union the set containing 3, and this of course is going to give us back the set 1, 2, 3, which is A. And so we have that 1 is satisfied. That's good. Next we move to, is F pairwise disjoint? To be pairwise disjoint, we have to consider every set in F such that x is not equal to y, and we must satisfy that x and y are both disjoint. But that's a problem, because if we take 1, 2 and intersect it with 2, 3, we are going to get back the set containing the element 2, and therefore this here is non-empty. And so now this fails. So F is not pairwise disjoint. And so it is not a partition. So let's look at G. So in the case of G, we will have that the union of G is equal to A, because now we're taking the union of the empty set with the set containing 1, the set containing 2, and the union with the set containing 3. We're going to get back A. Good. By inspection, we have that this is pairwise disjoint. We take the empty set intersected with the set containing 1, that's empty. Set containing 1 intersects set containing 2, empty. And similarly for the rest of the other combinations we have. We have that for every x and y in G, such that they are not equal, their intersections are empty. And so we do have that 1 and 2 are satisfied. So G, union of G is equal to A, and G is pairwise disjoint. But now we are in trouble with the last statement, because the last statement is saying that for every x in G, x is not equal to the empty set. The empty set is in G. So third condition fails. Since the empty set is in G. So G is not a partition. And finally, we come to H. And so with H, we do get that this is going to be a partition. Once more, we see the union of H is in fact A. We only have two sets in H, but if we take their intersections, we have that this is empty. The set containing 1 intersection, set containing 2 and 3, that's equal to the empty set, so it is pairwise disjoint. Is pairwise disjoint. And lastly, we do have that the empty set is not an element of H, so H is a partition. So now that we have some familiarity with how this definition works, let us consider the two equivalence relations we considered earlier, congruence modulo M and the definition of the rational numbers. So, as a recap, we have our relation, and I'm only going to work on the left-hand side for now, and then we'll come to congruence modulo M in just a moment. So we have that R is our relation on our Q tilde, which is those collections. As a reminder, Q tilde, that's the collection of fractions A over B, such that A and B are integers, B is not equal to 0. But as a set, this is not the rational numbers because 1/2 is not equal to 2/4 in here. So we defined our relation, we showed that it was an equivalence relation, and we looked at Q tilde mod R, which is how we define the rational numbers, and that's the set of equivalence classes, X, and then our relation, X is in Q tilde, and this notation, the equivalence class of X, by definition, that consists of those elements in Q tilde, such that Y comma X is in the relation. Is this a partition of A? Well, sorry, let me rephrase that. Is Q tilde mod R a partition of A? So now, the first thing we need to know is this a family of sets of Q tilde? And it is, because by definition, Q tilde mod R is the collection of equivalence classes which themselves are subsets of Q tilde. Here we have it. We have our equivalence class of X. That is the set consisting of elements of Q tilde. And so in other words, each of these is a subset of Q tilde. So we do have that Q tilde mod R is a family of sets. And so we can look at what is the union of Q tilde mod R. But this is going to be equal to the union as we go over all the possible equivalence classes, where now our union ranges over all those x's in Q tilde. But in taking this union, since we're going to be taking unions of sets of these equivalence classes, and we're ranging over all the possible x's in Q tilde, this is going to give us back Q tilde. Now, let's look at if it's pairwise disjoint. So we have to take two elements that are not equal. So for example, in our illustration earlier, we have that 1/2 under this relation is the same as the equivalence class for 2/4. And so these are equal elements in Q tilde mod R. And so we want to take two non-equal elements and then ask if we take for every two non-equal elements, are they going to be pairwise disjoint? And the answer is going to be yes. We do have that X R intersect YR, that this here is going to be empty if the equivalence class for x is not equal to the equivalence class for y. And we'll come to that in just a moment. But we can see it with an example. If we took 1/2, the equivalence class for 1/2, and we took the equivalence class for, say, 1/3, the 1/2, that's going to be the collection of all fractions that are equal to 1/2. So 2/4, 3/6, so on and so forth. Those are all the elements in this set. If we take 1/3, that's going to be the set of all elements that are equal to 1/3. And so we're going to have 1/3, we're going to have 2/6, we're going to have 3/9, so on and so forth. And so the elements of the equivalence class of 1/2, the equivalence class of 1/3, they're going to be disjoint. And lastly, these are all going to be non-empty. And so I'm skimming over quite a bit, but we're going to prove a theorem in just a moment that this is what we are building up to. We just having this concrete example. And so we can, so with some work, we can show that F is pairwise disjoint. I mean, Q tilde mod R is pairwise disjoint. And the last condition follows. And so lastly, Q tilde mod R is a partition. And if we consider the integers modulo m, we will have the same exact situation. So I'm going to go ahead and just verbally walk through this and then go to the main theorem in the next slide. So if we consider the integers modulo m, this is also going to be a family of subsets. This is going to be a family of sets where all these equivalence classes are themselves subsets of the integers, just as with Q tilde. When we take the union of the integers modulo m, and so this notation z, so this notation here, we can say it this verbally as z modulo m, the integers modulo m, or z mod mz. That's a notation that is referred to in abstract algebra. So I'm going to use this phrase z mod mz or the integers modulo m when discussing this. So that's a family of sets. When we're taking the union, what we really are doing is taking the union of all those x's and the integers, where now we're taking the union of the equivalence classes under the integers modulo m. And this here is going to just be equal to the whole set of integers. Now, the pairwise disjoint property is going to be in the case of the integers, we can see this from the division theorem. The division theorem tells us that there is a unique remainder. When working with the integers modulo 5, I made the comment that we can view this as the set of these 5 equivalence classes. The equivalence class of 0, equivalence class of 1, all the way to the equivalence class of 4. And each of these are pairwise disjoint. The empty set is not in here, so we do get back that the integers modulo mz is a partition. Is a partition of the integers. And of course, I have not proven these results in this case. This is just meant to be an example because there is nothing special about the relation R or the integers modulo m that is unique to that relation. This is a property that holds in general whenever we have an equivalence relation. And so that's what we are going to do. We are going to prove this for any equivalence relation. And that warrants why we have not proven it for these two cases separately. So before proving our main theorem, we need a lemma. Suppose R is an equivalence relation on A. If X is in A, then X is in the equivalence class of X, and this holds for every X in A. Now, one thing, so far we have been using the notation equivalence class, and then we have a subscript R to refer that the equivalence class corresponds to the equivalence relation R. When R is clear from context, we just drop it. And so in this case, this bracket X, we infer that this is the equivalence class of X with respect to the equivalence relation R. And so that's our first statement. The second statement tells us that for every X and Y in A, if Y is in the equivalence class of X, then that is equivalent to the equivalence class of Y being equal to the equivalence class of X. So what I'm going to do is sketch only one direction of this argument. The book does the whole proof, and so I'm just going to go through the scratch work for doing to the forward direction. And so in this case, we have that Y is in the equivalence class of X, and we want to prove that this implies that the equivalence class of Y is equal to the equivalence class of X. So how do we go about this? Well, the givens are that Y is in the equivalence class of X, but by definition of the equivalence class of X, that is the collection of those Z's in A such that Z is related to X. So, in other words, Y being in the equivalence class of X is telling us that Y is related to X. So now, with that, let us show that Y, the equivalence class of Y, is equal to the equivalence class of X. And so we're going to do an element chase here. So let us go ahead and take a Z to be in the equivalence class of Y. By definition of the equivalence class, we have that Z is related to Y. So we got that. But we know that Y is related to X. And so now we use the fact that R is an equivalence relation, so it is transitive. So now Z are Y, and since we have Y are X, R being transitive, since it is an equivalence relation, implies that Z is related to X. Therefore, Z is going to be in the equivalence class of X, because this consists of all those W's such that W are X. So W is being related to X. So we got that. So this shows that the equivalence class of Y is a subset of the equivalence class of X. Conversely, we can choose a Z in the equivalence class of X. So then, that tells us that X are, order matters. In this case, it does not matter since it is an equivalence relation, but I'm going to go ahead and write this as Z or X. So we know that this is the case. But we do know, again, by assumption, Y is related to X. So by assumption, Y is related to X. But the relation is an equivalence relation, so it is symmetric. So since R is symmetric, we have that X or Y holds. And now we use transitivity again. So now we have Z R X, X R Y, and since R is transitive, we have that now Z is related to Y, and thus we have that Z is in the equivalence of class of Y, which shows that the equivalence class of X is a subset of the equivalence class of Y, therefore they're equal. And so that's the idea for that direction. But again, for the converse, where now you assume that these are equal, then Y is in the equivalence class of X, I leave it to you to look over what the book does for that proof, or as an exercise, give it a try on your own. Now that we have the lemma, we can prove the main theorem of the section. So suppose R is an equivalence relation on a set A. Then A mod R is a partition of A. Now, in this proof, I'm going to prove the case when A is not equal to the empty set, and I leave it to you to check the empty case situation. Remember that at the end of the last video, we discussed how the empty set is always transitive and symmetric. But if the set A is non-empty, it is not reflexive. But now if the set A is empty, then the empty set as a relation becomes an equivalence relation. And so that's a case that does have to be considered for the theorem. And so I leave it to you to try that out. I'll work on doing the case when it's non-empty. And so here's the proof. So if we want to show that A mod R is a partition of A, we need to show these three properties. So let's go about this. So now, so by definition, we have that A mod R is the set of equivalence classes of X, where now X is in A. And so that's our definition. We have that, and X is equal to the set of Y's in A such that Y is related to X. So we got these two. So let us consider the union of A mod R. So we first show that the union of A mod R, which is equal to the union of all the x's in A, is equal to A. And so now this here is by definition. So these are both equal, so we want to show that these are the same. So what we are going to do, as is the case, is choose a y in here and show that that y is an element of this. But in this case, we actually don't have to do that much. So observe that so by definition, we have the equivalence class. That is always going to be a subset of A. So this is a subset of A. And thus, when we take the union of all these x's in A, of all the equivalence classes, that will be a subset of A as well. And so what we need to do is show the reverse direction. So we need to choose a element of A and show that it's in the union. So conversely, let Y be in A. Then if we apply the lemma, so by lemma 4.5.5, Y is an element of its own equivalence class. So in particular, Y is in A mod R, because by definition A mod R is just a collection of all the equivalence classes. Oops, sorry, I meant the brackets, not the element. So the equivalence class of Y is an element of A mod R, and thus the union of A mod R is in fact equal to A. And so that shows the very first statement. So next up, we have to show that R is pairwise disjoint. And so for that property, by definition, we need to choose two elements of A mod R that are not equal. So next, let X and Y, the equivalence class of X and the equivalence class of Y, be elements of A mod R such that A, the equivalence class of X, does not equal the equivalence class of Y. And what we want to show is that the intersection of both of these is empty. But now, if we consider lemma 4.55, since this is an if and only if, we have the following. So by lemma 4.5.5, where now we are going to apply the contrapositive twice. So the contrapositive, let me just put it in here, by the contrapositive of lemma 4.5.5, we have that X, the equivalence class of X, being not equal to the equivalence class of Y, is equivalent to the negation of this here. So now Y is not an element of X. So we have this here. So with that in mind, let us go ahead and consider the intersection. So we claim that the intersection of the equivalence class of X and the equivalence class of Y is equal to the empty set. So we're going to do a contradiction. So towards a contradiction, suppose that the intersection were non-empty. So then there is some element Z in that intersection. So we have this element here. But now if this is the case, then we have that Z is in the equivalence class of X and Z is in the equivalence class of Y. Now by definition of an equivalence class, we then have that Z is related to X and Z is related to Y. And now we use symmetry and transitivity. Since R is symmetric, we have that X RZ holds, and thus by transitivity of R, we get that X RY holds, and hence we get that Y is in the equivalence class of X, which contradicts our inclusion of lemma 4.5.5. And so this is our contradiction, which is a contradiction. Consequently, we have that X intersect Y is non-empty as claimed, which shows that A mod R is pairwise disjoint. lastly, we consider the third statement that we need to show that this is a partition. So let us go ahead and take an x in A mod R. Now, by definition, we have that x is equal to the equivalence class of y for some y in A. In particular, x is non-empty. And now that finishes the proof, because now we have shown each of the three statements. So we conclude that A mod R is a partition of A. And that finishes it for the main theorem. And so now, what about the reverse of this? What if we had a partition, some family of sets that was a partition of A? Can we construct an equivalence relation R so that that family of sets is equal to A mod R for that equivalence relation? And so that's the question I leave you with, and we will tackle this in our next video. So in particular, the only part of 4.5 that has not been covered today is the material pertaining to theorem 4.5.6, lemma 4.5.7, lemma 4.5.8. So in the textbook, in the next lesson, we are going to go over page 221 through 223 of the text. And we are also going to discuss strong induction. And so that's the goal for Wednesday's lesson.